Okay, Suhail,
Yeah.
okay, so we are very happy to have Suhail Sherif talking to us. It would have been much nicer to see Suhail after a long time over here. Anyway, Suhail was is a past PhD student of ours, and he works in computational complexity theory, mostly in communication complexity, but now I see he's doing high-dimensional combinatorics. Yeah, he will say some interesting stuff. Over to you, Suhail.
Right. Thanks, Sherif. Thanks, everybody, for coming in person and on Zoom. This is a talk in high-dimensional combinatorics, but it also uses communication complexity, so I'm still there somewhat. And it's a very interesting talk. It deals with some very basic objects from additive combinatorics, and we'll see. So the introduction of this talk is going to take probably half the talk, because there's a lot of lore and background to these things, which I find very interesting and I don't want to skip out on. And then in the second half of the talk, I'll focus mostly on our contributions. And by our, I mean, this is joint work with Liana, Tony, Morgan, and Adi. Now, in this talk, we'll be dealing with sets that don't have certain subsets. So our focus eventually is going to be on sets that don't have high-dimensional corners. But for the first 15, 20 minutes, we won't need to go into what a high-dimensional corner is. We'll be working with arithmetic progressions. So over here at the bottom, I've included a fun fact, which is that if you take all numbers that in base 3 only have the digits 0 and 1, then this set does not have any 3-term arithmetic progressions. And it's not hard to see why, but we're not going to go into that now. But this is what I mean by being free of 3-term arithmetic progressions, is that you can't find 3 distinct elements of the set which are in an arithmetic progression. Now, this is a very important concept to us, so we're going to give it some notation. So by Rk of n, I mean the largest subset of the integers from 1 to n, which does not have a k-term arithmetic progression. And interest in this quantity goes back a long time. And one of the most important first results in this field was this theorem of van der Waarden. So fix any constants c and k. K here is the same k, so it talks about k-term arithmetic progressions. So we're fixing a k and we're fixing a constant c. And the claim is that if you split the numbers from 1 to n into just c subsets that partition it, at least one of these subsets is going to contain a k-term arithmetic progression. So this theorem states that it's hard to find, it morally states that it's hard to find large subsets which don't contain arithmetic progressions. To make this a bit more formal, we'll also consider this quantity, which is the minimum number of colors required to color the numbers from 1 to n, such that every color is individually free of k-term arithmetic progressions. So over here, I've drawn the numbers from 1 to 27 and colored them with 4 colors, and none of the colors here contain a 3-term arithmetic progression. So in terms of this coloring number, this van der Waarden's theorem basically says that this coloring number must be super constant. As n increases, the number of colors that you need to use does need to increase. And although this coloring concept is very nice, many combinatorialists were more interested in this question, which is, what is the size of the largest set? And it feels like these statements should have something to do with each other. Indeed, if the second statement is true, that the largest set free of k-term arithmetic progressions is subconstant in density, then you need more than a constant number of colors to color 1 to n. So this part is pretty simple to see. The other part is kind of true. So what we want to know is, if you need a large number of colors, which is the first statement, does that mean that the largest set is actually small, which would be the second statement? So we'll be proving the contrapositive here, saying that if there is a large set that's free of k-term arithmetic progressions, then you can actually color the whole set with just a few colors. So here, assume that this rectangle is the universe, and over here we have a set which is large and free of k-term arithmetic progressions. Now, if you add any number to the set, that is, you translate the whole set by any integer, it'll continue to be free of k-term arithmetic progressions. And that's really the only thing we'll be using here. And now we're asking how many shifts of this set do I need in order to cover my whole set from 1 to n? Now, it's clear that I will need at least n by r sets, where r is the size of this large set here. But with the probabilistic argument, you can show that if you take log n times that many shifts, you are going to, with non-zero probability, cover the entire set. So this says that the coloring number is at most a log n times more than what you would think it is based on the largest set size. So if this first statement was instead saying little omega of log n, it would imply the second statement. But unfortunately, this statement is proven through Ramsey theoretic methods. So it's actually like omega log star n. So it doesn't actually imply the second statement yet. So study of the second statement dates back to this paper of Erdos and Turan. And along with the observation of Zacharias, they show in this paper that, well, they don't show that you need subconstant size, but they show that if your set size is at least half of 1 to n, then it does contain a 3-term arithmetic progression. And the fun fact that we saw on the title page shows that there actually is a somewhat large set of at least polynomial size in n. So they conjectured that since, that's a very neat construction and it seems to be optimal for small numbers, they conjectured that that actually is the optimal size set, that it's polynomially smaller than n. But the bounds that they had were between polynomial and constant. Then a few years later, Salem and Spencer showed an even larger set. So they constructed a larger set not containing 3 APs. And let's choose a different color. So if they had proven that this was at least n times 2 to the minus c log n for some constant c, this would have just been a polynomial size, because minus c log n makes the second term inverse polynomial. But what they showed is that this thing was actually larger in the sense that it's not a constant here, but you have a log n. So they've gone past polynomial. Now it's somewhere between, now the question of where does this value lie is somewhere between super polynomial and constant. Then shortly after that, Wherein improved this further, saying it's not just this small super polynomial, it's in fact significantly past polynomial. And so this log n by log n was improved to square root log n. And this was generalized a couple of decades later by Rankin, who generalized this not just for 3-term arithmetic progressions, but for k-term arithmetic progressions. So if you want to avoid k-term arithmetic progressions, it should be an easier task. And they showed that, yes, you can actually get much larger sets compared to Rankin, compared to Wherein, if you're looking at larger arithmetic progressions. Now, on the other side is the question of, can we actually show its subconstant density? That was proven in 1953 by Roth. This is a breakthrough result. So he showed that it's at most n by log n, and there were some improvements to make it n by log n, but very recently there was a breakthrough which showed that it's not just n by polylog n. The correct format of the answer looks very similar to what Wherein had. So this
is that a ninth?
Sorry?
Just curious, is that a 9th root there? Or?
Yeah, that is a 9th root. So they don't quite get the square root log n, but it's referred to as the shape of the answer is this shape. It's some root of log n in the exponent. This statement has not yet been generalized to longer arithmetic progressions. And what we know for longer arithmetic progressions is basically n by log n, effectively. So this is the background for the combinatorial part, as far as arithmetic progressions are concerned. And we'll be taking a closer look at this construction of Wherein, which will be important to us later on. But before that, does anybody have any questions? Feel free to interrupt me. Any doubts or clarifications?
So, remind me, Zemira's theorem, which is little o of n. You're saying
Yes.
less than little o of n. So, what was the quantitatively, what kind of bound would you have gotten?
So
A?
I'm not absolutely sure if I'm remembering this correctly, but I think it's like n by log n to the there's some exponential in k here. Not exponential in minus k. I think it becomes close to n by log n to the 0. That exponent becomes 0 as k increases, but it's still non. Yeah, that's the structure of it, I think.
Okay.
All right. So we'll be looking at Barron's construction now. It's a very neat construction. So this is a fun slide. Oh yeah, I should mention here that Barron didn't actually prove it's minus 2 root 2 square root log n in the exponent. There was additional terms, but those were lower order terms compared to square root log n, so I will be ignoring those. There have been improvements to this by improving on the lower order term, but if you're only looking at the highest order term, this has not yet been improved, both for this and for the Rankine result. All right. So Barron's construction starts with an observation that if you weren't looking at integers, but you were looking at vectors, then this problem becomes somewhat easier. There's a trick to handle this. And by vector arithmetic progressions, I just mean this. So 3 vectors form an arithmetic progression if the difference between the first and the second is equal to the difference between the second and the third, exactly like it is for integers. So if you think about them as vectors, it also means that in every coordinate, you have an arithmetic progression if you just limit yourself to that coordinate. And some of these di's can be 0. That means you could have the same entry in a specific coordinate, but at least one of the coordinates must have a non-zero di for them to be 3 distinct vectors in an AP. So why are these easier to avoid? Well, if you look at all the vectors of a specific length, so here SL is every vector whose squared length is equal to L. This is free of 3 APs. You cannot find a 3 AP of vectors which all have the same length. And that's because if you think of vectors of the same length, that's like saying they all lie on the surface of a sphere. And any line through a surface of a sphere can only intersect it at 2 points. So you can't have 3 points in a line all on the surface of the same sphere. So it's a very easy way to find, to group these vectors in a way that every grouping is 3 AP free. Another way to think of this is that this quantity v square is in some sense a quadratic polynomial. It's a quadratic expression, and saying that there are 3 vectors in a line which all have the same length is like saying there's a quadratic polynomial which takes the same value at 3 different points and is a non-constant. So that's another way of seeing that it's impossible. But yeah. So what does this mean for us? So in the case where Q over here is just like a constant and D is approximately log n, this gives us n vectors, and the number of possible lengths that you can have is going to be, the smallest length you can have is say 0, and the largest length you can have is Q squared times D. Or the largest squared length you can have is Q squared times D. And so with these parameters, this is just like order log n many different lengths. And so with a pigeonhole-like statement, you can say that at least one of these sets has size at least n by log n. So it's in this sense that you can find large sets of vectors that don't have arithmetic progressions. The problem is that we want integers, not vectors. So for this, we note that integers can actually be treated as vectors. And that is, if I think of x just being an integer from 1 to n, in terms of its base q representation, so here let's assume that n is approximately q to the d. So if you write its base q representation, that's a vector, a d-dimensional vector. Unfortunately, there's a problem here. If you take 12, 18, and 24, that's an arithmetic progression. But if you look at the vectors that represent them, they don't form a vector arithmetic progression. So the vector arithmetic progression would actually be these three vectors. But because of the carry in the last case, what you actually get if you write the base Q representations is this different vector over here. But if you only think of numbers whose vector representations have small entries, then this is not a problem. That is, if you take three numbers that form an AP, and if you look at their base Q representations, each of these three numbers have only small entries, then in fact, these three vectors are going to be a vector arithmetic progression. This is also somewhat easy to see, but we won't go into these details now. We might see them at the end of the talk if we have time. But with this extra property, now we can just think of only these integers. That is, integers which only have small entries in base Q. And the number of such integers from 1 to n is going to be like n by 2 to the d. For every coordinate, you're throwing away half of your integers. So you still have n by 2 to the d integers, which have the property that if you look at their vector representations, if the three integers were in an arithmetic progression, the vectors are also in arithmetic progression. So if we take d to be around square root 2 log n, then the number of such integers that we have is a fraction of, its fractional size is 2 to the root 2 log n. Since we're looking at the base Q representations, over here, we'll be putting Q to also be around 2 to the square root log n. And so the number of lengths here would also be something like 2 to the square root 2 log n. So over here, we lose a 2 to the root 2 log n factor. Over here, we lose a 2 to the root 2 log n factor. And so, okay, so I'll just repeat this once more just to make sure we know what's happening. We're taking only those integers which have small entries in their base Q representation. We're looking at those vectors of base Q representations, and then we're looking at only those vectors of a specific length L. And since there are no three arithmetic progressions in those vectors, we know that there's no three arithmetic progression in the integers from which those came. So therefore, this gives us that R3 of n is at least n times 2 to the minus root 2 log n times another 2 to the minus root 2 log n. And that's exactly the construction of parent. So not all of these details are going to be important later on, but it's important that what we're trying to do is we're trying to find out, change these integers into vectors, and then use the simple logic in the case of vectors.
Suhail, so when the fun fact you gave in the beginning, where we were looking at things in base 3 representation, where we just had zeros and ones.
Right.
That seems to fit this template as well. But then there is no restriction on the fact that you want all of them to have the same length or something.
That's true. So it doesn't actually, like, the reason why things work there but not here is, so it feels like it's very much the same framework, but it's actually not.
Oh.
So this is not a generalization of that. This is a significantly different construction. Yeah. Okay. Now, okay, so now what's the time? Let's see this. Okay, so now we're going to see corners for the first time. We're done with our background on arithmetic progressions. They'll be important later on, but let's move on to corners. And here we're asking the same question, but now in higher dimensions. So a KAP was basically the set 0, 1, 2 till k minus 1 scale. Oh, yes.
Sorry, just so this Barron's, I think so Barron's construction is still the best known construction, right?
It's still the best known construction.
I mean that Raghu Meka et al. Gave that ninth root thingy.
That's enough. Yeah.
Yeah. But I'm just saying there's no matching, like
Yeah.
the amount is not dipped below, right?
Yeah, it is not.
Yeah. Okay. And there are no other constructions. Like this length trick is the only thing that we know.
Right, yes. Yeah, there have been some improvements on wherein, but on the lower order terms, which just like fine-tune this argument a bit to be able to extract a little bit better, but it's the same idea.
Taking vectors of same length to avoid AP is the only idea that we know, right?
Yes, that is true. So an arithmetic progression is basically, it's a set of equally spaced integers. So you can think of it as just the set from 0 to k minus 1. You're scaling it by some amount to keep it equally spaced. And then you're translating it to say that it doesn't have to start from 0. It can start from any point. So pictorially, a 4-term arithmetic progression looks like this. It's just 4 equally spaced dots in 1 dimension. Now, a k-dimensional corner is another simple shape, but it's not in 1 dimension. So over here, we take the origin and we take the k-axis vectors, the unit vectors along each axis. And then we're scaling this by some integer and translating it so that it doesn't actually have to have the origin as a point. And so basically, it'll always look like this, where the lengths of each of these arms is the same. So for instance, this is a 3AP, 17, 23, 29, which is just 17 plus 6 times our basic set. And here's a 2-dimensional corner, which is 3 points. And it's this, this is the new origin, 5, 8, and we've scaled each of the arms by 7. So very easy definition of what a corner is. And we'll be interested in such shapes, which are basically scaled and translated versions of a base shape. And this ties into this whole framework in multidimensional Zemerides theorem, which is proven by Furstenberg and Katz-Nelson using ergodic theory. So they say that let F be any finite set of vectors in d-dimensional space. And we can similarly define this quantity, which is what is the largest subset of this d-dimensional grid that actually avoids this shape. So anything of the form v plus d times f. Okay, this should not be d over here. D is the dimension. V plus c times f. Well, so if we define this quantity, Rf of n, they prove that it has to be of sub-constant density in order to avoid this shape, whatever this shape is. So it's a very impressive statement, and it's since been reproved in many different ways.
So should we think of little d as a constant here, or should we think of it as a goal?
Sorry, think of what as a constant?
Little d compared to capital N.
Oh, little d is a constant, yes. F is a fixed shape. So since it's a finite set, n doesn't appear until this
Okay.
So sorry, so this is not the corner. I mean, I thought for the corner this that's F had to be
right. So for a corner, we'd want the specific set F.
That pattern, right? This is a more general thing. I see.
This is a more general statement. It says whatever F is, you will have subconstant density.
Right.
And you have to have subconstant density. So Tau calls this the Rosetta Stone of mathematics, in the sense that this theorem has been proven through many different methods. And by looking at the various proofs of this theorem, you can find connections between those methods, which is a cool fact. Yeah. But so why did I mention corners if this works for any generic shape? So let's define, let's just use this notation similar to the AP notation to just be when F is actually a k-dimensional corner, we'll put a corner symbol in the superscript and k in the subscript to denote k-dimensional. And then if you can actually prove that just for corners, the statement is true, that corners alone need subconstant density, then in fact, you have proven it for all shapes. So even though this multidimensional Zemerides theorem sounds more general, it's sufficient to prove it just for corners in order to prove the whole statement.
What's the
So
relation?
What's the relation between K and D?
Yeah.
K and D.
Like if you are looking for a full dimensional corner in D or
Oh, I see. All right, here. So K and D. So a K-dimensional corner has K plus 1 points. So D would be K plus 1. Yeah, I think this is true in general. If you just prove this statement not for all K, just for a specific K, this will imply it for all F of size. Oh, sorry. So it's not D. So it's for all F such that the size of F is K plus 1.
No, but what is the relation? His question still stands.
No. I guess Pavel's question is like, suppose you are working in an ambient dimension of D.
Yeah.
The corners you are trying to avoid also D-dimensional corners, or are you trying to avoid a smaller dimensional corner where K is like
I see what you mean. No, so when we talk about corner free sets, our ambient dimension is always the same as the K here. So D is equal
to D. Yeah.
K is equal to D. Right. Yeah, I didn't understand that question. Right. So, yeah, the statement that I've just stated here says corners are the most general case, so they're interesting in that sense. All right. So why is this true? Why are corners the most generic shape? And that's because if you take any K point shape, if you start with a K minus 1 dimensional corner, which is K points, there is an affine transformation that will take your corner to that shape. And that's just because the K points in the corner are linearly independent or affinely independent. And we'll see an example of this. In fact, we'll see it with arithmetic progressions. So let's take this transformation, which I've denoted L. So this transformation, it takes K minus 1 dimensional vectors, and it spits out a single integer. So that is, it's a map from K minus 1 dimensional space to 1 dimensional space. And it maps the 0 vector to the number 0. It maps the first unit vector to the number 1, the second unit vector to the number 2, and so on. And it maps this K minus 1 dimensional grid to numbers between 0 and K square n as a rough upper bound. And it has this property that if you take a corner, a K minus 1 dimensional corner, then its K points will map to K term arithmetic progressions. And that's just because of linearity. Like the base shape over here, right? So this is the base shapes mapping, and the base shape maps exactly to our K term arithmetic progression set. So therefore, for any scaling and translation, which is basically the set of corners, any corner is going to map to a K term arithmetic progression. So how do we use this affine transformation? So here we have on the left side, so this is just an representation. It's not actually this transformation L, but on the left side, we still have a grid, and we're mapping it to a one-dimensional space. And if I can color the one-dimensional space in a way that it avoids, say, 3-term arithmetic progressions, then if I take these colors and just pull them back, this gives us a coloring of the grid that avoids corners. Because if you had a corner all of the same color in the grid on the left side, we know corners map to 3 APs. So you would find the 3 AP with all the same colors on the right side. So if you can color the right side avoiding arithmetic progressions, you've already colored the grid avoiding corners. So the number of colors needed to color in this grid avoiding K minus 1 dimensional corners is at most, the same argument would work for any shape. So the number of colors is at most the number of colors needed to color the right side, which is coloring while avoiding the shape.
So we are not able to parse this here. Sorry, you are.
So I have, so this mapping, is it, it's not like it's distinct points need to go to distinct points, right?
It's not by you.
That is true, but that's not a problem. So for instance, I've included that here.
Yeah, so
This
my
point
worry
is-
was, then can it happen that you have a not trivial corner on the left, but that
Yes.
gets mapped to a trivial AP on the right, in the sense that it's just 3 points which are the same.
Right. So that can't happen because of how our transformation works. Because like the base set of corners maps to the base set of arithmetic progressions.
Okay.
But nevertheless, that doesn't come in the way of concluding that if you have a coloring
Uh-huh.
of which is free from AP,
Uh-huh.
then the corresponding color. Oh, because how
So
do you
that
map
would
the
not be
colors?
it. Yeah, exactly. So that was my question. So in the sense that, yeah, but I guess Suhail's point is that it can't be the case that legitimate corner on the left gets mapped to
Trivial.
yeah, trivially to the right. Okay.
And what is this FK? Sorry.
So this was just in general if you had a shape F. So FK over here corresponds to K square. Because we're coloring on the left side the grid of size n, on the right side we're coloring this one-dimensional space of length K square times n. So it's not exactly coloring with the same parameter n. The n changes because of our transformation, but it changes by a multiplicative constant that's independent of n. It just depends on our mapping, which is only on K points. Did that make sense?
Yeah.
All right. Right, so we'll be ignoring all these constants that pop up. They're annoying to deal with in real life, but for this talk, we'll just ignore these constants.
The reduction is that if you construct large corner presets, that implies large AP presets. Is that the data?
No, it's the other way around. So, so in terms of coloring, it's simpler. If you have a few number of colors on the right side, you have at most that many colors on the left side. So in terms of largeness of sets, so it doesn't directly translate to largeness of sets, but it's also true for largeness of sets. If you have a large 3 AP free set, that gives you a large corner free set. Proving that requires a little more work, but
So that
it
means,
also changes some parameters. Sorry?
that makes sense because that means proving the lower bound on how large a set can be before it starts having corner. That might be an easier job, right? Proving a lower bound.
So constructing larger 3 AP presets may be a harder problem.
So constructing larger corner free sets would be easier.
Oh, so then what I said.
If you prove an upper bound on, so for instance, if you take the multidimensional Zemradius theorem, if you prove an upper bound just for corners, that is the most generic upper bound. That proves it for everything. So it should be harder to prove lower bounds for corners compared to proving lower bounds for arithmetic progressions. Sorry, this is an upper bound. Yeah, there's a problem here that lower bounds and upper bounds change as you talk about different quantities, but proving this statement that I've underlined should be harder for corners. All right.
No, that means if I proved that a
Yes.
particular set of a certain size has a corner, right?
Yes.
That means that the linear transformation of that set in the way that you just described, that particular set must have a
Yes.
term AP, right?
Yes.
Yeah, so it's a stronger result in that sense.
That is correct. Yes. Yeah, so that is also the same as this. You're showing that any large set must contain a corner is the kind of statement that I've underlined here. The largest set is of subconstant size.
Mhm.
Right. Right, and since corners are like this most generic shape, it seems like corners and APs should have completely different answers to this quantity. How many colors are needed to color the left side and right side? It should be much less for corners than it is for APs, is at least what I feel, since corners are so powerful.
So,
But
actually, so there's another thing, this Hales-Jewett theorem, right? Which
Yes.
is talking about a combinatorial line.
yes,
And, I mean, that's the Hales-Jewett theorem is the generalization of van der Waals theorem. Yeah. If you can show that there is a combinatorial line, this can be, I guess the transformation is similar now that I remember it, right? I mean, to get from a combinatorial line to an arithmetic progression, you do this kind of linear transformation that you were showing. So what is the connection between combinatorial line and these corners?
well, right now I'm not actually seeing that, because with the combinatorial line, you have to have like the full grid size, right? Your line has to completely traverse the grid size. But that's not kind of a,
Yeah, that's true.
but that's not a necessity here. Our shapes are always finite shapes, and n is growing, and you're trying to avoid the finite shape. So I'm not sure what the connection is. I don't think it's a same
Yeah.
kind of object.
Yeah.
All right, so as far as quantitative bounds are concerned on these upper bounds, there have been some. We know that two-dimensional corners, there is a upper bound like n squared by log n. And for k-dimensional corners, we also get a upper bound, but it degrades much more quickly. It has Ackermann-like behavior in terms of the quantity. But that makes sense, because proving this kind of statement is harder for corners. But finding large corner-free sets should be much easier. Now, despite this should be, what we know about large corner-free sets is basically what we know about large arithmetic progression-free sets. That is, so I'm just using this as a proxy for coloring. The corner-free set that you get from a 3AP free set, from Barron's 3AP free set, is essentially the best that was known. And similarly for Rankin, the largest k-1 dimensional corner-free set basically came from k arithmetic progression-free sets. Well, until communication complexity entered the picture, which was just a couple of years ago. So for a long time, as far as constructions were concerned, APs and corners, we didn't have a separation.
But corner-free sets were, to be just fair, just wanted to understand, corner-free sets were independently looked at by combinatorialists, is it?
Yes, I would say.
Not by combinatorialists who had their hands burned in communication. Like, okay, anyway.
Corner-free sets were looked at in terms of at least the things on the left side, that is upper bounds, not constructing large ones, but to prove that they can't be two large ones.
Okay.
Yeah, so at least on that side, it has been studied. It might have also been studied to find large ones, but there weren't any improvements until communication complexity ends. I don't know what the actual story is. There were no publications, at least, that were improving things. So what is the communication complexity connection? Let's see. So how much time do I have left?
15 minutes.
Yeah. How much time do you need? Would 20 minutes be okay? I mean,
20 minutes would be better.
I was just going by the clock. That's okay.
Okay, so I'll try to do a bit. I won't spend too much time on this, on the proof of the connection. So in communication complexity, we have a bunch of players. They all have inputs, and they want to compute some function of their inputs. So for instance, the equality function asks, are all our inputs the same? And we're working in the deterministic setting. They're not using random coins or anything. And we know that the equality question is hard. You need, if these were n-bit strings as the inputs, you need n bits of communication, or omega n bits. The question we're interested in is equality, but with an extra promise. So if their inputs are all equal, they have to output 1. But they're promised that if their inputs are not equal, they're still coming from this set script f here. So script f does not contain, does not contain a tuple which is all the same. I've not written that down, but it's implicit. And we have this promise that if your inputs are not equal, they're in fact from this set. And that should make things a bit easier for our players. So
Well,
if you can actually...
Sorry. Are you now, what is the model of communication? Because you've drawn multiple players. Is
There are
it?
multiple everyone can see their own inputs. They can't see anybody else's inputs.
Oh, okay.
And whenever they speak, everyone can hear what they're saying. So it's the blackboard model. Number in hand.
Number in hand.
Right. So say that their inputs are coming from this set X. If you can color the set X with C colors in such a way that it avoids this set, by which I mean that if you take any 4 elements from X that are not all the same, and they're all of the same color, then that does not belong to the set F. Right? So if you can actually color X in this way, then you can actually solve this problem with just around log C bits of communication. Player 1 will just announce what the color of X1 is according to this coloring. If everybody else sees that their input also has the same color, then that actually means that their inputs are all the same. Because if their inputs were not the same, but they all had the same color, then since our coloring avoids F, that means that their input could not have belonged to F. So it would be a non-promised input, which is not possible. So therefore, their inputs are all the same. But the connection isn't just this direction. The reverse direction also holds. If you can solve this communication problem with just C bits of communication, then you can actually color X with just 2 to the C colors in a way that avoids F. And that's because of this property of communication that if on 2 different inputs you have the same transcript T, that is, if you look at exactly what was communicated, that's the transcript. Then if you also mix up their inputs, you create a new input by just mixing up these 2 instances, that will also result in the same transcript T. That's basically because all the information that you learn about the other inputs comes just from the transcript, and you can't really distinguish between them if you had the same transcript in both cases. So now what you can do is you can color the element X with the transcript of the protocol when its input was just all X's. And if you have 4 different Xi's which have the same transcript, then that means that because of this transcript property, that you'll have the same transcript even on X1, X2, X3, X4. But the output over here has to be 1, and the output over here has to be 0. And if the transcript is the same, then that's not possible. So if you actually have a correct communication protocol, then you cannot have 4 different Xi's which all have the same transcript. Okay, so this is the connection. So this kind of coloring problems can be equated with communication complexity problems.
So
basically,
Suhail, what are we coloring, X to the 4 or X or?
Oh, you're coloring X. So X is just each of the inputs X1 comes from a set capital X, which is why script F is a subset of X to the 4. So if you think of this as just X being integers, you can think of F as just being all 4-term arithmetic progressions, but you're still coloring individual integers. So what this says is that if you can compute this complexity of this promise problem, that tells you exactly what the coloring number is up to an additive constant. All right. So this is just a connection between generic coloring problems, not specifically corners or any arithmetic progressions. But the connection with corners comes in this weird model, which is the number on forehead communication model. So here a player cannot see their own input, but they can see all the other inputs. And they want to compute this function here, which is the sum of all our inputs equal to a specific number n. So this was introduced by Chandra first and Lipton, who also in this paper introduced this model of communication. And you can think of this, even though it's a different model of communication, you can think of it as a normal communication problem where you can see only your own input and not others' inputs. It's just that you have to change it so that your input is now everything that you see. You're just defining it this way. So player 1 sees x2, x3, x4, and the other players see correspondingly what they see. Now, I'm going to define a very small protocol which doesn't solve this problem, but which changes the problem. So the first step of the protocol is every player privately comes up with a fourth input. And they define this fourth input in such a way that the sum of all their inputs is actually equal to n. So the question is still, does x1 plus x2 plus x3 plus x4 equal n? So this fourth input is really useless, but let's just make all the players assume that they have this fourth input. Now, the reason this is useful is that you can rewrite what they've done over here. So if n prime is the actual sum of the four inputs that we care about, then what they've computed here, what player 1 has computed over here is exactly x1 plus n minus n prime. Similarly, player 2 has computed x2 plus n minus n prime, and so on. And the second step of the protocol is to ignore, say, your last input. This is a completely reversible process. If you've ignored it, you can bring it back just by knowing that the sum of all your inputs is equal to n. So these two steps that we've taken does not change any of the information that anyone has. It's exactly the same problem, this problem and the original problem. But if you see what they've done here, they've transformed their input into a corner. If n is actually equal to n prime, if exactly n is equal to 1, then all of them have the input x1, x2, x3. But if n is not equal to n prime, that is, if they should actually be outputting that exactly n is equal to 0, then they actually have a corner. This is the origin of the corner. And here we've added n minus n prime times e1. We've added n minus n prime times e2 and n minus n prime times e3. So essentially with this protocol, what they're saying is that solving exactly n is exactly the same as solving this problem where each person is given a vector and they want to know whether their vectors form a corner or whether all their vectors are equal. So it's equality with the corner promise. I realize this was a bit fast, but this is an important connection. So finding a better protocol for exactly n is the same as finding a better protocol for the equality with corner promise, which is the same as finding a coloring of vectors that avoids corners, which again is the same as finding a large corner preset. So that's the connection between communication and our problem. One more thing I want to mention here is that, so over here, after this transformation, everybody has a vector and they form a corner. Now, if everyone applies the transformation L to their input, they'll end up with, this is the same transformation that we saw earlier, they'll end up with an integer. So let's say A1, A2, A3, and A4. If all their vectors were the same, they would all have the same integers. And if their vectors are not the same, which means that they started with a corner, then they have an arithmetic progression. So this is the communication version of corners are hardest. If you want to solve this problem for corners, you can solve it by a reduction to arithmetic progressions. So solving for arithmetic progressions is easier than solving for corners. Okay. So this is just a recap. Wherein created a large 3AP free set. because of our relation between set size and coloring, this means that there is a 3AP free coloring. Because of our reduction to corners, there is a coloring that's free of two-dimensional corners. And because that's equivalent to this exactly n communication problem, this means that there is an efficient protocol for three-player exactly n. And if you follow, we have follow the numbers quantitatively. We basically get that the cost of this is 2 times square root log n. Now, all of this is existential. And 2 years ago, Lanial and Schreibman released a paper in which they constructed an explicit protocol for this three-player number on forehead exactly n problem, which had the same cost as this implied protocol. So its cost was...
This is existential because there was a probabilistic method in the second or something step or something.
So, right. So there's a probabilistic method to go from set size to coloring.
And that is why it is existential.
That is right. Yeah, that's the only reason it's existential. That's not.
Okay,
Yeah.
thank you.
So after constructing this protocol, since it's a communication protocol and it's easy to think of communication as parties trying to exchange information, they actually managed to improve the protocol to get a better bound of 2.402 times square root log n. And so this was the first improvement on large corner-free constructions. So these parts are if and only if. Oh no, sorry, this is not if and only if. These parts is if and only if. Right, so they actually created a better protocol over here, which means that they created a better corner-free coloring over here. So you have an improvement in the constant in the exponent.
So then, going from 1 to 2 incurs this extra factor of log n or something, right?
Right, yes. So I should actually be saying that this number of colors should technically have a times log n here.
Okay, but that doesn't affect any of the higher order terms.
Covering.
Right. It's lower. It just becomes log n in the exponent. So I didn't mention that, but yeah, this should be plus log n. And after this paper, there was, within a few months, another improvement which followed the same lines, but written combinatorially, which improved it further to 1.822 times square root log n, which is the best, which is currently the best known protocol cost for NOF exactly n. All right. So we, in our paper, it's nearing the end of the talk, but finally reached what we do in this talk, in this paper. We do the same thing for larger, that is KAP free sets. So Rankin had a KAP free set, which had some constant over here, which I'm not writing down because it's very messy. You can do the exact same steps and say that means that there's an efficient protocol for this K-player number on forehead exactly n. And we construct an explicit protocol that matches that cost. And then we use some number on forehead tricks to improve it by a small multiplicative factor here. So we decrease the exponent with it. And this can be seen as a generalization of Green's improvement, but to these problems. Now, I'm not going to touch the explicit protocol construction. That's fairly simple to see, but the NOF tricks, I will try to tell a little bit about in the next 5-10 minutes, if that's all right. Okay. So I'll skip this slide. Right. All right, so the protocol for exactly n, what it does is, we know that exactly n is the same as corners, this corners promise problem. And we know that corners can be solved by solving this arithmetic progression problem. Okay. And in Barron's construction, what he did was he started off with integers, and then he restricted himself only to those integers that have good base Q representations. So he went from integers he went to vectors. And he wanted these vectors to form an arithmetic progression. And this step, if you look at it in a communication sense, it costs d bits of communication. And what we're going to do is we're going to bypass these two steps in a way that costs less. And to be more specific, what we do is we go from exactly n to a vector version of exactly n. So we bring in the vectors in the number on forehead setting. And then from vector exactly n, we go to vector arithmetic progressions. Right. So this was a number on forehead problem. This was a number in hand problem. What we're doing is, while staying within the number on forehead setting, we're going to get a slight improvement. So what is this vector exactly n? Everybody has a bunch of, everybody has a vector as input in the number on forehead setting. And they want to know, does the sum of these equal to some target vector? Right, so this is the question. You have, so we're trying to solve exactly n now. So is the sum of these inputs exactly equal to n? The first trick is to rephrase this in such a way that the carry isn't really a problem when you look at the base Q representation. So what we're going to do is we're going to rephrase it as, is the sum of the first k minus 1 inputs equal to n minus xk. So the kth player can see all of these numbers that we're adding up. And this is going to be important. So when you change these integers to vectors, you can add them up as vectors, but because of carries, there might be a problem. So we also want to add in a carry correction to make sure that the carries don't cause a problem. And this carry correction, it only depends on the numbers that we're adding. So it only depends on the numbers from x1 to xk minus 1. And player k can actually see what this carry correction should be and communicate it to the other players. So here's a simple example. We're adding up 3 numbers. This is how we do it. We add it up and then we put up the carries over here. What these carries are really saying, it says add up your numbers as if they are vectors, and then add these specific extra vectors to make sure that your final number is a correct base Q representation. So all that player k needs to do is add these k minus 1 vectors, or add these k minus 1 numbers, find out what this carry vector is, and then tell the other players what the carry vector is. And once the other players know what the carry vector is, they can just add up these as vectors and add these up as vectors and ask, is it equal to this target vector, which is an instance of vector exactly n. So that's exactly how you can think of this communication protocol. So you've found an instance of vector exactly n, where x1 to xk minus 1 are just the base Q representations. But the kth player's input is now the vector representation of n minus xk minus all of these carry correction vectors.
So so when you add the values in the least significant coordinate, yes, a carry is generated, but the carry need not be a single digit carry, right? It can be a multiple digit carry. Meaning
right. So over here, we're going to be assuming that k is actually constant and q is growing much.
Okay.
Right. The carry will never actually be more than k. Right. So that's why this carry is in k to the d.
Got it. Thanks.
But the problem with this is we wanted to bypass the d-bit communication protocol that we had, and we've ended up with a d log k-bit communication protocol that creates vector exactly n. So this isn't an improvement. If anything, it's the opposite. But we can do other tricks that improve upon this. And the second trick, which wasn't required in the 3-player setting, is going to be this. So we're going to use the fact that every player can see all inputs but their own. So suppose you're this last player here who can't see this input, but you can see the other inputs. We can do most of the addition ourselves. 5 plus 6 is 11, plus 5 is 16. So we know that whatever carry is over here, it's either a 1 or a 2, because the answer over here can range from 16 to 25. So we know that this is 1 or 2. So if the kth player just tells me what the parity of this carry is, that's enough. If they just tell me, hey, this carry is even, then I will know that the carry is actually 2. I can add 2 plus 6 plus 5 plus 9, find out 2 possibilities for this carry. Again, I have the parity of this carry, so I know which number it is, and I can just continue. So if you're just communicating the carry modulo 2, now you're only communicating d bits, 1 bit for each of these. So it still hasn't improved upon our original protocol, but at least we've gotten back d bits. We're no longer worse than before. And now we need one final trick, which again, we're borrowing from Daniel and Strideman and Green. And that is basically, well, we would think of it as a way of encoding the carry. If you can encode the carry in less than d bits, that would be very useful. But it's not exactly that. So let's take the example here where we have 3 numbers, and let's assume these 3 numbers are random. If you add up these 3 numbers, the number that you get over here will have this distribution. It's between 0 and 3q, and it peaks at 3q by 2. Over here, the carry is going to be 0. Over here, the carry is going to be 1. Over here, the carry mod 2 is going to be 0. So if you look at what the probability is that the carry modulo 2 is 1, it turns out that this is larger than half. It's half plus some constant larger than 0. And this is true again for the second column. You might be adding a carry here of, say, 1, but since q is much larger than 1, that doesn't matter. So the distribution over here is also can be treated as the same distribution. So the most probable carry that we're going to get if we have 3 random numbers is the all 1 carry. So let's just take this set S of all numbers such that the carry modulo 2 is the all 1 string. Well, this set has size, since each coordinate has probability half plus some constant of being 1. This set has size significantly larger than 1 by 2 to the d. So the distribution of carries modulo 2 is not uniform. And so there should be some way to compress it a bit, but we're not going to compress it. Instead, what we do is player K, who can see all of this happening, who can see what the carry actually is going to communicate a set of numbers such that if every player shifts their input by the corresponding number, the resulting input actually has carry equal to this all 1 string. So instead of communicating what the carry is, player K is instead telling everyone to shift their numbers, saying if you shift your numbers, you'll get a different carry, and that carry is going to be this all 1 carry, which is something you can only think of in the number on forehead setting. And so the new question that they're asking is this: is the sum of my new numbers equal to n minus xk minus the summation of whatever numbers I've added on? So this is a new exactly n problem, except that now we already know what the carry is. The carry is the all 1 string. And this is more efficient now, because if you think about, so suppose player K communicates this specific string, delta 1 to delta k minus 1. Which inputs does this string work for? Well, that is actually going to be exactly S minus this delta 1. So it's really a shift of S. If you shift your S, the whole set S, by exactly this amount, the set of inputs that you get are exactly the inputs for which this shift works, because it gets you back inside S. So now the question of how much is player K communicating here is the same as how many shifts do I need of the set S in order to cover my whole space. And that is, again, by the same probabilistic argument we saw at the beginning. That's going to be basically n to the k minus 1 divided by size of S times log of n to the k, or n to the k minus 1. So this is the number of shifts that are required. And for player K to specify a shift, you only need log of this many bits. And so if you see what that is, that's going to be log of this number's larger than half to the power d, plus a log n term, which we'll ignore. And so this is actually going to be d times 1 minus a constant larger than 0. And so with this third trick, finally, you've become better than the previous thing. So these are the 3 number run for tricks you need in order to actually get a better protocol than the original non-number run for protocol. So this leaves the question of what is this quantity here, these advantages. And this is another contribution of our paper. We'll skip this slide. Right. So it turns out that if you look at the polynomial expansion of sec x plus tan x by 2, the coefficients of x are exactly the advantages that pop up. And we have a proof in our paper. It's not a proof that I understand, but it's a proof that's verifiable. So this is one of our contributions, is saying that these, what are called the Euler zigzag numbers, that's what these coefficients are, or they're related to the Euler zigzag numbers. We've shown a connection between that and the probability that a sum of a certain number of numbers has a specific carry modulo 2. I think I'll just say a little bit about what happens if you have, instead of 3 numbers, if you have 2 numbers. So if you have 2 numbers, the carry is equally likely to be 0 or 1. So the advantage you have is actually 0. But if you add a third input, you just act like there's a new input here which has all entries equal to q by 2, then you shift it. And in this shifted distribution, the advantage is actually larger than 0. So that's another trick. This trick comes from Ben Green, and it's very useful for us. Okay, sorry I did not time that well. I had to rush a bit at the end, but that concludes the talk. We believe that there should be more NOF tricks that we can use because we think that corners should actually be much easier to create large sets for. Finding a lower bound for exactly n, we were finding better upper bounds. Finding a lower bound is another very interesting question. It has applications to circuit complexity. And another question which would have made more sense if I had shown the explicit protocol for Rankin is to fill in gaps between powers of 2. So the construction of large sets that Rankin gets is really the same for KAPs, where K is between powers of 2 and it jumps at every power of 2. It'd be interesting to have a more smooth growth of largeness. All right, that is my talk. If there are any questions, I am free. I have more time to answer these or clarify other things.
What is the known lower bound for exactly n?
So the lower bound for exactly n is basically our lower bounds for corner-free colorings. So that's basically, it's as good as just saying it's a super constant lower bound. We really don't know much.
But the general belief is that square root log n is the right answer.
For exactly n, I don't believe that. I don't know what the general belief is, but I don't think people believe that square root log n should be the right answer.
No, but at the end of it, sorry, I got a bit. So what, show us, if you don't mind, one more time, what do these NOF tricks, what did this finally achieve?
Okay. All right. So
Constant before the Rankin.
Yeah. But I want to just look at that. There was a ranking.
what is the final result?
Yeah. The final result, that, as I said, what was the improvement in the ranking now?
Right. So Rankin's bound is, well, improve Rankin's bound, but not in the AP setting, in the coloring setting. So Rankin had this. Oops. So Rankin created a large AP-free set of this size, which meant that there's a KP-free coloring of also this number of colors. Okay, so what our result would say is that you don't actually need these many colors. You only need 2 to the CK times 1 minus epsilon K times the same log Kth root of log n.
Okay.
So another peculiarity here is as K increases, that's basically every player is seeing more information because they can see K minus 1 inputs out of K inputs. So you would assume that the improvement becomes better as K increases, but this epsilon K actually goes to 0. So the improvement is better for the behavior of this is something like 2 by pi to the K. The improvement grows weaker exponentially fast.
Any other question? But by the way, sorry, one other thing. I mean, I think Raghu, when he was here, he did say that, but this new paper it does not give any not yours, but the maker.
Right.
There's a third author option. K.
So the number on forehead paper.
Huh?
Is it the paper relating to number on forehead or the paper relating to arithmetic progressions?
No, the number on the forehead, the second one. Yeah.
Okay, yeah.
That does not give any bound on exactly n, right?
Right, yeah. It doesn't work with exactly n.
Meaning it fits anything super constant, any super constant load. It does not use any super constant.
It's a technique that doesn't apply to exactly n. They need some kind of pseudo-random properties for their result, and exactly n doesn't have those kind of properties.
Okay, I don't have any questions. So. Okay. Thank you, Suhail.
Thank you.
Thank you. Thank you for having me. And